Oh, they're doing it. No, that's what time. I don't know. Maybe. Yes.
It's a pleasure to introduce Ciprian Manolescu from UCLA. He's going to talk about homology, cobordism, and triangulations.
Thank you. It's a pleasure to be here. So my thesis was also published in JDG, so it's an honor to be at this conference. My talk today will be more about topology, so I'll try to keep it elementary, although there is some differential geometry in the background. So I'll talk about the homology cobordism group, but first, yes, I'll talk about some motivation for studying it, which comes from triangulations of manifolds. So let me start by saying that so a triangulation of a topological space, it's a homeomorphism from X to a simplicial complex. And the first question about triangulations was raised by Poincaré in the second analysis situs. So in modern language, he asked if every smooth manifold has a triangulation. This was not exactly how he formulated it. So he had, he constructed manifolds as zero sets in Euclidean space, and then he also talked about spaces obtained by gluing polyhedra. So the latter now are the same as the space. I mean, it's easy to see that they're the same as triangulated spaces. And he actually tried to give a proof of this fact, but it wasn't fully rigorous. Still, the answer is yes, and the rigorous proof was given around 1940 by Cairns and Whitehead. So they showed that every smooth manifold has an essentially unique piecewise linear structure that is compatible with the smooth structure. Yes. And if you have a piecewise linear structure, then you can actually get a triangulation. Now, a more difficult question is about topological manifolds, and this was asked by Kneser in 1924. By that time, people formalized the notion of a topological manifold, and so unlike smooth manifolds, in smooth manifolds you can approximate a smooth map by a linear map, so you might expect a piecewise linear structure, but for topological manifolds, you don't have this kind of thing. Still, I think Naser believed the answer was yes, but it turned out to be no. So let me say a little bit about the history. There are two versions of this question. So you can ask about arbitrary triangulations, but you can, but somewhat more natural is to ask about triangulations coming from piecewise linear structures. So these are usually called combinatorial triangulations, but I don't really like the name. Like all triangulations are something combinatorial, so I'm going to call them PL triangulations. All right, so what's the precise definition? So a triangulation is called combinatorial, or PL, if the link of every vertex is piecewise linear homeomorphic to a sphere. So let me remind you, the link of a vertex in a simplicial complex is you take all the simplices that contain the vertex, then you take the closure of that, and then you remove the simplices that contain the vertex, and you get whatever goes around the vertex. And if that's a sphere, then of course, locally the space looks like the cone on a sphere, which is Rn, so it's a manifold. And these are the kind of triangulations where you can see when the structure of being a manifold is apparent from the triangulation. Yes, and it's not too hard to see that these are equivalent to piecewise linear structures on the manifold up to isomorphism. All right, so these are kind of the triangulations you see in nature. But interestingly, and this was not clear for a long time, but it turns out to be the case, that manifolds can also have non-PL triangulations. So even though they look locally like Rn, the link might not be a sphere. So here is one example. The standard example is to take a homology sphere with non-trivial fundamental group. So you could do the Poincare sphere in dimension 3, but great. And then you take the suspension of it, which, so let's assume M is triangulated, and then you get a triangulation on the suspension. So you take two cones, and then you take the suspension of that, the double suspension of M. Right, and so that's something of dimension 2 higher. So this is a difficult theorem, but it was proved by Edwards and Cannon in the 70s that the double suspension is homeomorphic to the sphere in dimension n+2. So yes, it's kind of hard to describe the homeomorphism. But if you believe their theorem, then you see that this is a non-PL triangulation of the sphere. So the one obtained by triangulating this and then taking cones in both directions and then further cones. And the reason for that is that if you look at the link of this vertex, this is this sigma of M. Yes, and sigma of M, well, is it a sphere? Well, M is not a sphere, and sigma of M is also not a sphere. In fact, it's not even a manifold. I mean, one way to see this is if you take a point out of sigma of M, this vertex, then around it you get, it looks like M, so it's not simply connected, but if it were a manifold, and you take out a point, it should be simply connected in a neighborhood. Right, so yeah, so you can ask about triangulations in general, including this more complicated case, or you can just ask about PL triangulations. Okay, so let me, so the first story that was clarified was for PL triangulations. And in dimension at most 3, then everything is nice. Every topological manifold has a unique smooth and a unique PL structure. This was, well, for 3 manifolds, it was proved by Moyes in the 50s. It's also a difficult proof, but yes, the result is simple. In dimension greater or equal than 5, this was the next case to be settled, and yes, this was it's a much more interesting story. So it's the results are due to Kirby and Ziebenmann around 1969, and they were based on earlier work by Sullivan and Casson. So first of all, it turns out that there exists topological manifolds that do not have any piecewise linear structures. And in fact, you can characterize which manifolds are piecewise linear by what's called the Kirby-Siebenmann invariant, which is an obstruction class in the fourth cohomology with Zima2 coefficients. So yeah, so they define such an element, and M has a piecewise linear structure if and only if that obstruction vanishes. And furthermore, they have a classification. So if they exist, then PL structures are classified by elements in the cohomology in dimension 3. And this is, so this is the failure of the famous Hauptvermutung for manifolds. So the Hauptvermutung said that every triangulations of the same space have a common subdivision. And this was disproved by Milnor for some topological spaces that are not manifolds. But this is, for manifolds, it turns out to be kind of equivalent to whether the triangulations give the same PL structures, and since you have more PL structures, you can have, if H3 is non-trivial, you get triangulations that do not have a common subdivision. Okay, and dimension 4 is special, as always. So by combining the work of Donaldson and Friedman in the 80s, yes, so in dimension 4, smooth and PL are the same thing, and such structures may not exist and may not be unique. But yes, it's still, well, they're still not classified. So a conjecture is that there's infinitely many on every smooth manifold in dimension 4, but yes, it's not known. Okay, so this is the story for PL triangulations, and now you can ask the same for arbitrary triangulations. Dimension 4, well, in dimension 4, right, so in dimension less or, in dimension less or equal than 3, then everything is fine. They have triangulations. In dimension 4, so Friedman showed that the E8 manifold, he constructed this E8 manifold, and he showed it was not piecewise linear, it was not smooth. But Casson later, a few years later, using his invariant, could show that it's also non-triangulable. It doesn't have any triangulation. And in fact, nowadays that we know the Poincaré conjecture, it turns out that that all triangulations are PL in dimension 4. So it's the same as before. Okay, so dimension greater or equal than 5, this is what, I'll talk about for a little while. So before saying the answers, let me explain the idea. The idea. So we're going to look at the links of simplices in codimension n+1. So sorry, n is not the dimension of the manifold. Let's say m is the dimension of the manifold. And we take a simplex and we take the link of that simplex if there is a triangulation. Let me go back a few slides. So here, for example, so I defined before the link of a vertex, but you can also take, say, the link of a simplex. Again, you look at the simplices that contain it and then take the closure and eliminate the ones that contain it. For example, the link of this edge is M itself. And M, notice that M is a homology sphere, but it's not a sphere. So this can happen. So yeah, so to study arbitrary triangulations, we're going to look at the links of simplices. So it's not hard to show using just homology theory that they are homology spheres. But they might not be spheres. And it turns out that we can rephrase the questions about triangulations in terms of what's called the homology cobordism group. So this is what, this will be the object of my talk, but I wanted to give this motivation. So that's where, the impetus for studying it comes from. So what is the homology cobordism group? So you can define it in any dimension. It's generated by homology spheres. So yes, with an orientation, and then you divide by an equivalence relation, which is given by, well, two homology spheres are equivalent, homology cobordant. If there exists a PL, I guess you want to say homology manifold, Wn plus 1, with, so a cobordism with the boundary being y0 union y1, and which looks homologically like a cylinder. So the relative homology is 0. Okay, so this is a group, and it turns out that, yes, this kind of, when you subdivide or change triangulations on the same space, the links kind of change by homology cobordism. So they are homology spheres, and they change by homology cobordism. So, yes, so you're interested in this group. But it turns out that it's only interested in dimension 3. So a theorem of Kerver shows that it's 0 in all other dimensions. So this is using the H-cobordism theorem, and then, of course, in dimension 3 and 4. I mean, this is really about dimension 4. The cobordisms are 4-dimensional. There are some glitches, and you get something non-trivial. Right, so let me tell you what we know about the 3-dimensional homology cobordism group. So, yes, so as I said, in dimension 4, you can, instead of PL, you can think about smooth cobordisms. And, right, and the first thing that was known about this is the Rochlin homomorphism. So this is a homomorphism to Z-mod2. It's given by the signature of a spin 4-manifold with boundary y divided by 8 mod 2. So Rochlin's theorem says that the signature of a spin 4-manifold, the closed spin 4-manifolds, is divisible by 16. If it has boundary homology sphere, then it's divisible by 8, but the parity just depends on the boundary. And it's an invariant, so if two homology spheres are homology cobordant, then they have the same mu. So mu of S3 is 0, but mu of the Poincare sphere is 1, because the Poincare sphere bounds the E8 plumbing, which has signature 8. So this tells you that, that theta 3z is non-trivial, unlike the other groups. So what else do we know about this? So, well, it was proved in the 90s using Yang-Mills theory by Furuta and Fintuschel-Stern that the group is infinitely generated. It has a Z infinity subgroup. And, well, if it has a subgroup of some type, it doesn't necessarily mean that it has a summand of that type. It does have at least a Z summand by work of Freishov. But it's still not known if it has, well, I mean, it's an abelian group. Maybe I should have said so. Right. So theta 3z, it's an abelian group. You can look, I mean, connected sum is addition, and changing the orientation is minus, and 0 is the sphere. So it's an infinitely generated abelian group. We don't know if it has torsion, and perhaps it's actually Z infinity, but as far as I mean, it could also be Q infinity plus Z or something. So yes. Okay, so now let me say what's known about triangulations of manifolds in dimensions at least 5. So these are arbitrary triangulations. So for PL manifolds, Kirby and Siebermann had these 3 results, saying that there exist non-PL manifolds, and you can say which ones they are based on some abstraction class, and if they have a structure, the structures are classified by something. So in the 70s, Galuski, Stern, and Matsumoto had a similar list of results, but it was somewhat incomplete. So what did they prove? They proved that, so with regard to the existence, yes, and you're looking at arbitrary triangulations, there exist non-triangulable manifolds in dimensions greater or equal than 5, if and only if this exact sequence, which is in terms of the homology cobordism, so we're looking at theta 3z, and the Rochlin homomorphism and the kernel does not split. So yeah, if you can't find a map going the other way, such that when you compose it to mu is 1, right, and this remained an open question if it splits or not. So what I proved a few years ago was that it does not split. So such non-triangulable manifolds do exist. Right. So what does it mean that it doesn't split again? It means that there does not exist anything in the image from z mod 2 to theta 3z. So splitting would be given by an element in here that's 2 torsion because it comes from z mod 2. And mu of it should be 1. So there is no 2 torsion of Rochlin 1. So later on, I will say a few words about the proof. Now, with regard to which manifolds are triangulable, that's another interesting question. So they showed, they had an analog of the Kirby-Siebenmann obstruction, which lives in H5 of M with values in kernel of mu. So this is an index 2 subgroup of theta 3z. So this is a very complicated group. In fact, in particular, we don't know what it is. I mean, we don't know what theta 3z is. So the obstruction is not, it's not very explicit. But actually, it follows from their work that you could get a better obstruction in H5 of M with z coefficients if you knew something else, namely that theta 3z had no torsion with mu equals 1. So what I proved here was that it doesn't have any 2 torsion with mu equals 1, but in principle it could have some 4 torsion. So this remains an open problem, and well, at the end I will mention some strategies to attack it, but yes, it's still open. So yeah, right. So if this was true, which sounds very likely, then you could say that a manifold is triangulable if and only if some explicit obstruction class in the fifth cohomology vanishes. And then they also had something about the classification of triangulations, if they exist. So they are classified by H4 of M with values in kernel of mu. In this case, you cannot replace it by Z. I mean, that's the classification up to concordance. So this gives some motivation for studying theta 3z. So one thing you want to study maybe is torsion with mu equals 1, but you also want to know what the group is, in particular what is its index 2 subgroup. And then that would tell you how many triangulations you have on a manifold. Okay, so for the rest of the talk, I will discuss, so this was motivation, but now I will discuss what we know about theta 3z. So this is about homology spheres and about 4-dimensional cobordisms between them, which can be, well, in principle, they're piecewise linear, but that's the same as smooth. So smooth 4-dimensional topology is understood there are 2 methods, either gauge theory or symplectic geometry. Well, by which I mean Hagar-Floer homology, which is secretly also gauge theory. Okay, so basically there are these 3 theories, Yang-Mills. So this was the original theory used by Fintuschel, Stern, and Furuta to show that the group is infinitely generated. So I will not talk about their methods so much. Let me just say that they use the Chern-Simons functional and its values. And then what I'll talk about is Cyborg-Witten theory and Hagar-Floer homology. And so these are the more modern methods and what we can get from them. Okay, so let me start with the Cyborg-Witten equations. So, these are a system of nonlinear partial differential equations. It's elliptic modulo gauge, and they are very useful in dimension 4. They're sensitive to the smooth structures, just like the Yang-Mills equation, so they can be used to say distinguish smooth structures on the same 4 manifold. I won't write them down for now, but let me just say the following. So if your manifold has a spin structure, then you get, so in principle, they have a symmetry. They have an S1 symmetry. So you have the, it makes sense to not divide by the whole gauge, but by the base gauge group, and then you still have an S1 worth of symmetries. And you can have reducible solutions or irreducible solutions under that S1, so it's better to keep the S1 in the picture. Now, if you have a spin structure, you have an additional symmetry, this J, and if you combine it with this S1, so again, S1 are the constant gauge transformation, yes, then you get a group which is pin 2 inside the quaternions. You can think of it as 2 copies of S1, very explicitly S1 union JS1 inside the quaternions, where J squared is -1. So this is it's a non-abelian group. It's an extension of Zima 2 by S1. Okay, so to get the full equations from the to get the full information from the equations, you want to take into account this symmetry. So in dimension 4, you kind of count solutions and get numbers. In dimension 3, there are different constructions of Cyborg-Witten-Floer homology. So you can do an analog of Morse theory in infinite dimensions using the Cyborg-Witten equations. So Kronheimer and Mrówka have a book on this, and there are some alternate constructions for maybe just for rational homology spheres by Freushov and Marcoli Wang. And what I did was also for rational homology spheres, you can do slightly better than a homology. You can do a stable homotopy type. So this is by a technique introduced by Furuta, finite dimensional approximation. And you can right, so you can define a stable homotopy type whose homology is the Cyborg-Witten-Floer homology. All right, so now so my focus for today is how to get information from this homology and homotopy types about the homology cobordism group. So this is not how this information came about initially, at least not all of it, but in retrospect, all the invariants that are relevant for homology cobordism that come from Cyborg-Witten theory can be obtained by a particular homomorphism, namely by factoring through what's called the local equivalence group, which was introduced by my student Matt Staffragan. So let me explain what that is. So I claim that there exist some homomorphisms of abelian groups from theta 3z to another group called LE, and then if you want, you can just take chains and get CLE, chain local equivalence. So these are some interesting groups, but, well, they seem to be simpler or easier to study than theta 3z. So kind of like the theme for my talk is that we should think about these groups instead. They're still very interesting, and we don't understand their structure. So what are these? Well, let me tell you what the homomorphisms are, and then I'll tell you what the groups are. So if you have a homology sphere, which is an element in here, you're going to map it to the Cyborg-Witten-Floer stable homotopy type. Right, so this is some stable homotopy type. It has a pin2 action on it coming from the symmetry. And if you want, you can also take the chain, the chain complex of that, let's say with Zima 2 coefficients. So you make a group out of that. You make an abelian group out of this. So what is LE? Okay, good. Yeah, so LE is made of pin2 equivariant stable homotopy types. But if you want, you can just think of them as spaces, satisfying a certain condition that their S1 fixed point set is a sphere. So this comes from the fact that in the Cyborg-Witten-Floer stable homotopy type, we know the S1 fixed point set corresponds to just reducible Cyborg-Witten equations. So those were, I didn't say this, but Cyborg-Witten equations are for a connection and a spinor. And the S1 fixed point set is when the spinor is trivial, and you can in that case, the equations become very simple, they're linear, and in fact, on a homology sphere, there's a unique solution, namely, yes, the connection has to be trivial as well. So you can understand the S1 fixed point set, and it turns out to be a sphere. And now you divide by an equivalence relation. So this is somewhat similar with the homology cobordism group, but it's made of their flirt spectra. So the equivalence is as follows. So two spaces, or pin2 spaces, are equivalent if you can find maps back and forth between them, which are pin2 equivariant. And on the S1 fixed point sets, they are equivalences. So they're not, so this is not like stable homotopy equivalence. When I say equivalence, I always mean stable homotopy equivalence. But you just want them to be equivalences on the S1 fixed point set. So, right, the reason for this definition is that this equivalence is modeled on what happens when you have homology cobordisms. You get maps like this between the corresponding Floer spectra. So Cyborg-Witten-Floer homology is kind of a topological quantum field theory. So you have, when you have a cobordism, you get maps. And furthermore, if it's a homology cobordism, then you can again, you can study what the reducibles are, meaning the S1 fixed point sets, and you get that they're equivalences. Right, so this is why you get such a map. Right, so, yes, let me also say, so why is this an abelian group? Well, yes, so, so this is kind of defined from stable homotopy theory. It has nothing to do with manifolds. But you can define addition as being smash product, and you can define the inverse to be the Spaniard-Whitehead dual, right, and the unit is just S0. And everything is based, I should say. Yeah, so the fact that the homology cobordism induces maps like this gives you this homomorphism. And then if you want, you can also take the chain complexes, and you can define a similar group here made of chain complexes, but you still want to use the pin2 symmetry, so they're going to be chain complexes over the chain complex of pin2. And I'm not going to say the definition, but it's very similar. So it's chain complexes over C star pin2 modulo some equivalence. Great. So kind of we can map from this to some groups that at least appear simpler. I mean, they don't have to do with manifolds. They're about stable homotopy or chain complexes. And from here, we can get numerical invariance. So the prototype, the simplest invariant of this form, is what's called the Froishoff homomorphism, and you can factor it through CLE. It's a homomorphism to Z. And it's obtained by passing, not just taking the chain, but taking the homology, namely the S1 equivariant homology. So this is the S1 equivariant Cyborg-Witten-Floer homology of Y. Yeah, so this was introduced by Froishoff before all this local equivalence. He just looked at the Floer homology. So the S1 equivariant homology is a module over the equivariant homology of a point, which is just a polynomial ring in one variable. So again, I'm working with Z-mod 2 coefficient. My F is a Z-mod 2, and the degree of U is 2. So Froishoff's definition is as follows. So one thing to observe is that I guess I'm doing cohomology. Let's do cohomology just for simplicity. You can do it with homology if you want. So this is Borel cohomology. And basically, there is one reducible and several irreducibles. And the reducible gives you a copy of f of u, so a copy of Cp infinity, which is like an infinite dimensional thing. And then there's some finite dimensional part, which is the fu torsion part coming from the irreducibles. And the Froishoff homomorphism is 1/2 the minimal grading of this part. So there is some grading that, yes, I didn't talk about, but yes, in Cyborg-Witten-Floer homology. And if you choose the minimal grading in the FU tower, this turns out to give you a homomorphism from CLE to Z. And therefore, it gives you a homomorphism from theta 3Z all the way to Z. And this is how you can get this result that the group has a Z summoned, because, well, you can compute that, let's say for the Poincare sphere, the value is 1 of delta. And if you have a, so therefore this is a surjective homomorphism. If you have such a thing, then you get a decomposition of theta 3Z into the kernel of the homomorphism and whatever has anything that has delta equals 1, so say the Z summon generated by the Poincare sphere. So, I mean, yes, so the moral of the story is that if you find homomorphisms to Z, then you get something about the structure of the group. And you get, well, we know how to get one such homomorphism, but you also have these other groups in here, so maybe if you knew more about these groups, you could get more information. Okay, so this was the S1 equivariant Floer homology, so we didn't use the full symmetry of the equations. Now, if you use the pin 2 symmetry, you can do the same thing as Freshoff did. So the pin 2 equivariant Borel cohomology of this space, of the Floer space, again, you can look, well, it's a module over the equivariant, pin 2 equivariant cohomology of a point, which is, well, you can compute what it is, and you get basically 3 infinite parts instead of 1 infinite part. And that gives you 3 maps to Z. Now, yes, for technical reasons, they're not homomorphisms. Yes, this is just because of algebra, because the cohomology of BS1 of CP infinity turns out to be a PID. But in this case, it's not a PID for pin 2. So you still get some maps. And one nice thing about these maps that was not true for the Freshoff map, was that they recover the Rochlin invariant when you reduce the mod 2. And although they're not homomorphism, they satisfy this symmetry. So when you change the orientation of the manifold, you get alpha of minus y is minus gamma of y, and beta of minus y is minus beta of y. So these are the maps that I used to prove this theorem that I mentioned, that there is no 2 torsion in theta 3Z with mu equals 1, and that implied the non-existence of, the existence of non-triangulable manifolds. So what does this have to do with this? So, I mean, it's, let's just go through this. So if there was some 2 torsion in theta 3Z, then you would get that y is homology cobordant to minus y. And then let's just use this invariant beta. You would get that beta of y is beta of minus y. And, well, by this property, it's minus beta of y. Now, this is an integer, so you get that beta of y is 0. And since it reduces mod 2 to Rochlin, you get that the Rochlin invariant is 0, and it's not 1. So, so that's kind of how the argument goes. And it's based on using the pin 2 symmetry of the Cyborg-Witten-Floer spectrum. Okay, so, oh yes, and I should mention, so Francesco Lin, 1 year later, gave an alternate construction of alpha, beta, gamma. So my construction used the Floer spectrum and finite dimensional approximation, but you can also do it using more traditional Floer theory, so kind of the Kronheimer-Mrówka style, and this gives another construction and another proof of this corollary. Okay, so let's review. We had theta 3Z, we could simplify it by doing something with stable homotopy. We could just take chain groups, and then we get homology theories, equivariant homology theories, and we get these maps, delta and alpha, beta, gamma. You could also look at other subgroups of pin 2. So this was corresponding to S1. You can look at Z mod 4, which is the thing generated by J, So recall J squared is -1 in the quaternions. There's a Z mod 4 living in here. And if you do that, you get 2 new maps to Z. And actually, it turns out that these are all of them. I mean, at least with Z mod 2 coefficients, if you use other subgroups, you just get other combinations of this. You don't get anything new. But you can get these 6 maps. Well, of this type, by taking the minimal grading of some power. Okay, but then you could not pass to chain groups. You could look at a stable homotopy, and instead of homologies, you can do other generalized homologies. So maybe K theory and KO theory, and again using the pin to symmetry, you can get some new invariants, kappa I and kappa OI. So the kappa 1 was I did, and kappa O is due to John Feng Lin. And these have, well, let me not say too much about them, but they have their own application, so you can use them to study the intersection forms of spin 4 manifolds with boundary. And they're also invariants of homology cobordism. Okay, so it's still an open problem to describe what these groups are, LE and CLE. And if we understood more about them, then we could understand more about theta 3Z. All right, so now the last 10 minutes, let me talk about Hagar-Floer homology. So that's the other method for studying such things. So Hagar-Floer homology was introduced by Oshwart and Szabo in 2001. To a closed 3 manifolds, they associated some abelian groups, or actually modules over f of u, hf hat, hf plus, hf minus, using Lagrangian Floer homology on the symmetric product of a Hagar surface for y. So you split your 3 manifold into 2 parts along a Hagar surface, and you take symmetric product, and then you do symplectic geometry on that. This is a replacement for gauge theory, for Cyborg-Witten theory in particular. So the symmetric product is the moduli space of vortices, so that's why it's related to the Cyborg-Witten theory. In fact, there's a precise relation. So by work of Kutlu-Hanley Taubes, or Taubes and Kolangi, Gini, Honda, it turns out that, let's say, HF plus is the same as, is isomorphic to some version of monopole Floer homology. This is the notation of Kronheimer-Mrówka, HM2, and HF hat is another version, HM tilde. And if you want it in terms of the Cyborg-Witten Floer spectrum, this is the S1 equivariant theory, and this is the non-equivariant homology. So these are the symplectic version, and these are the gauge theoretic versions, and they are isomorphic. Ty Lidman and myself proved this isomorphism between the 2 different versions of Cyborg-Witten Floer homology. Right, so what Oshwart and Szabo did is they found a symplectic analog of Cyborg-Witten theory with the S1 action. The advantage to this is that it's easier to compute than gauge theory, so you can draw diagrams, and for many families, there are various methods. In fact, it turns out to be algorithmically computable. This was work of Sharkar Wang from 2006, so they did this for HF hat. And then later, Lipschitz, Oshwart, Thurston found a better algorithm that you can actually put in a computer, and you can compute things with it. For HF plus, I did work with Oshwart and Dylan Thurston later, and we found some, we showed that that's algorithmically computable as well. But in practice, you usually want to compute it for some families, and you can do so by many other methods. So since these are replacements for the S1 equivariant theory, you can recover the same things that you can get from the S1 equivariant Cyborg-Witten theory, in particular the Froeshov invariant. This was, the analog was developed by Oshwart-Szabo. They called it the correction term, so using HF plus. And you can prove the same thing, that there's a Z summand. Okay, so more recently, in joint work with Chris and Hendricks, we try to find the pin-2 symmetry on the symplectic side, so on Hagar-Floer homology. So there's a conjugation symmetry, which kind of plays the role of this extra j. And using that, we defined some new invariants, which we call involutive Hagar-Floer homology. And they are supposed to correspond not to pin-2. So for technical reasons, we can't quite get the whole pin-2 symmetry. But this corresponds to the Z mod 4 subgroup of pin-2. And since it corresponds to Z mod 4, it can give these maps. Well, in this case, it's just a conjecture that is the same as Cyborg-Witten, but it definitely has the same properties. So you can get invariance from theta 3z to z. And you can use the power of Hagar-Floer homology, like all these methods. So we did some computations. I guess with Kristen, I first did large surgeries on alternating knots and torus knots, and then we had a connected sum formula in joint work with Hendricks and Zemke, and most recently in work with Dai, we computed it for ciphered fibrations. Now, what this gives, well, it doesn't quite give something about the structure of the group in general, but it gives more constraints on which three manifolds are homology cobordant to each other. So now you can compute the values of this invariance on various families of three manifolds, and if they're different, well, yes, then you know that they are not homology cobordant. And okay, so there is kind of one structural theorem, although it's a new proof of an older theorem. So as I said, the fact that the group is infinitely generated was due to Furuta and Fintuschel-Stern using Yang-Mills theory. And their methods were quite different, but it's kind of interesting that you can recover the same result using these extra symmetries in Cyborg-Witten theory. So this was done by Staffregen using the pin-2 equivariant Cyborg-Witten theory. And now we also have a proof using symplectic geometry, namely, yes, involutive Hagar-Floer homology. Right, so basically, you find some infinitely many generators, and you show that they are linearly independent by looking at connected sums and computing their invariants, del upper and del lower, and seeing that you cannot get linear relations between them. All right, so let me end with the simplest, what I kind of think is the simplest analog. So before I was advertising these groups LE and CLE. So in the Hagar-Floer setting, you can construct a similar local equivalence group, and it actually has a very simple form. So I wanted to give the definition here. So using involutive Hagar-Floer homology, you get a homomorphism from theta 3z to the following group. Let's call it J. It's made of free complexes over Z mod 2 of U, the polynomial ring in one variable, with an extra automorphism, which plays the role of the conjugation involution. So it's a homotopy involution. Iota squared is the identity. And you have a condition kind of on the fixed point set, namely when you take the homology and you invert the variable U, you should get this. This basically says that the homology has like one FU tower, which is what we saw for Cyborg-Witten theory as well. Right? Okay, so just complexes over this polynomial ring and with a homotopy involution and this condition, and modulo on equivalence that there are maps back and forth between these complexes. Sorry, maybe I should have said chain maps, but also module maps over F of U, such that they are equivalences when you invert the U. So this gives you a group, an abelian group. Addition is tensor product, and minus is the dual. And you have this homomorphism given by taking the Hagar-Floer complex and the conjugation involution. So the maps delta and delta bar and delta lower, they all factor through this group. And that's how you can get some information about theta 3z. But the open question is, yes, what is J as an abelian group, and can we use it to study theta 3z some more? In particular, there's still this open question whether there's torsion with mu equals 1. So we know there's no 2 torsion, but there might be some other torsion. And, well, yeah, I like this setup because it gives a very simple group. So let me remind you that chain complexes over a PID can be classified up to equivalence, and f of u is a PID. However, you have this extra automorphism, and that gives you trouble. So it kind of gives you a new variable, and then if you have two variables, it's no longer a PID, so you cannot quite classify them, but maybe you could understand them up to local equivalence. Okay, so that's all I had to say for today.
Any questions? Well, if not, let's thank Ciprian again.
Oh, hi, how are you?
Yeah.
Nick, right?
Yep, that's
right.
Yeah.
You're at MIT, right?
Yes, I am. Yeah.
How are you?
Good. Yeah.